machine learning. And so Python is a very popular language, and I came around when I looked for books, a local bookstore, and I noticed there was one book just for financial services programming with Python. And this is amazing, because usually you don't see that with such a relatively new programming language at it. And well, I must say I'm maybe a machine learning veteran, because I was in this field already in the beginning of the 1990s. There was the backpropagation was out then at the end of the 1980s. And so my background is electrical engineering, and then I went into computer science, into robotics and neural networks. And but after that I went out in different areas, but Python then brought me back into machine learning. And then trying out these libraries that are around there, then you really want to understand also, you want to look under the hood, what's really going on there, and you want to do it quickly. There is all of that stuff around there, and you don't want to overdo it, you want to quickly understand, and I want to understand then sometimes also down to the number, where is this number coming from? So Python has become the major language, the lingua franca, you could say, in machine learning. And there are many examples around, so you can easily just download some code and get it into your environment and start it. And it feels really like a kickstart. And so this presentation is about my journey, actually trying out different things and getting results and understanding them. So what I really like about Python is just the syntax. It's the clean syntax, and I think this is also why scientists, whether it's in biology or in aerodynamics or whatever, they really like this language, because you don't have to look for curly brackets all the time where they are matching. You just see it right away. You're forced to write proper code, proper looking code. And there's so much support for it. Okay, but then there are many different options, so you have to quickly make your decision. So how can I get it run? There's Jupyter network, there are Docker images and all of that around. But to get quickly started and not to be dependent on some networks connections, I just started downloading Python 3.6, because this is not the old track, so to speak, with Python 2.7 and so on. And 3.6 as well supported. I didn't go higher than that, because then you run into problems. And then also friends told me, okay, you have to try Anaconda. Anaconda is so great, you can do so many things. But I just wanted to start from the bottom and then work my way up. So Anaconda, I don't need that for the beginning. But I like integrated development environments like I'm used to from programming C, C++ or whatever. So, well, I got the hint that this PyCharm is pretty good, so it's for free also, so it's a good way to start. So this presentation is two parts where I'm digging into. So number one is the classification, text classification with k-means ++, and then we take a dive into deep learning also. So, first part. Anyways, whenever you want to classify text with a machine learning algorithm, the big part is building the feature map, getting the features out so you have proper vectors that you can classify. So I'm very thankful for the presentation, the introduction, the keynote, where this was explained also how these vectors look like. So normally they have values between 0 and 1, some normalized vectors. And so first of all, text is not numbers, so you have to convert the text into numbers, and then if you have the proper vectors that represent your documents, let's say, then you can build clusters. You can see, okay, which is similar, where are similar vectors, and there are standard algorithms, very old ones, and so one that is well supported is this k-means ++, which is also very popular. And then you can also use new text. You can put a new text into that feature map, see where that vector lies, and then you can say, okay, this is this cluster, this is this type of document, or the other one, like we saw before with the sentiment analysis, for example. This is the same goal. So it's
pretty much straightforward what we're doing here. We just need to import 3 libraries to get started. This is for the vectorization, this is to build the feature map. And then we have the k-means algorithm that we want. And then also another thing that we're doing, we are just importing an Excel spreadsheet writer. So what's behind that? Well, we can look at the numbers in a debugger, but sometimes it's just more handy, more explanatory to have the numbers in the spreadsheet, and then you can do your own calculation also in parallel, and you can check the numbers, and we show that in a while. So, just some data to play with, just keep it very simple. This is also like part of the Kickstart approach for me. I want to do simple things and I want to build up from that, and with simple examples I really know what's going on down to the number. So funny enough, Python, okay, what is Python? Python is a programming language, there's a Monty Python show, Python is a type of snake also, so I came up with these little sentences as examples, and then to see what kind of clusters I can build from that. So this is usually called the corpus. It's just a set of documents. Here just sentences, could be just different emails, could be different articles or whatever. But for simplicity, we just take sentences to start with. And now we build the feature map. And all of that comes with Python. And the thing is then, though, these libraries are highly optimized. So for computational speed, the libraries are usually written in C and C++, and they use a very compressed format for the data. So that means the data, the arrays are compressed, so sparse arrays. But then with sparse arrays, if you look at them at the debugger, you don't understand them. So this is why one of the tricks I learned here was then to convert them into a standard matrix, and then you can also understand what's happening. So look, this is, if you look at it in a debugger, but later we look at it in an Excel sheet. So, but we have to make sure then to just write the numbers into the Excel sheet, which is shown here. And also some other tricks are applied here. So so-called stop words are removed. So there are dictionaries of words that don't say anything, usually like the, of, or some prepositions like that. So they are removed. And then we can run the tokenizer and put everything in an Excel sheet. We will see in a minute how that looks like. So here we just predefine the number of clusters. We just say, for simplicity, we just have 2 clusters. And then we let the model run. We let the k-means ++ model iterate over all this data. And then we can get the cluster coordinates. So we can say we have these 4 simple sentences. It was about snakes, and it was about the programming language, basically. Or maybe it was about the show, also the Monty Python show. So, but we force then the algorithm to just identify 2 clusters. We don't say which is what. We don't label them. It's not supervised learning. It's unsupervised learning here. And then we convert that into a standard matrix and write that into a spreadsheet, just to get an overview what was really happening. And this is what it looks like then. So number 1, we see the algorithm extracted the words that are supposed to be relevant. So the, of, all of that is missing here. And then the single rows are our documents. So we see like the first sentence was about Python being a popular programming language. But then also, the interesting part is about this algorithm that we use here. It extracts the words that are most probably very important. They stick out. For example, programming doesn't occur very often, and popular doesn't occur very often, but it's occurring in the first sentence. So it gets a very high value in the first sentence. or first document. Here it's just sentences. And then we have something like Africa, Asia, and Australia, like down there. And in total, it occurs not very often, so it gets low values. I'm coming to the algorithm a little bit later in more detail to explain that. So this is the algorithm that builds our feature map. And it's used in many applications. Also, Google might be using it still, I guess. And so it says like a term that is in one sentence very often, but it's not very often over the whole corpus of documents, that gets a very high value. So this is the algorithm that is there. I know we are not in a math class, so I don't want to go into every detail. But this was my journey, so to speak. I looked up this algorithm from one of the examples that you find online, and this is just a summary, but I think you can all get the slides and then you see it there. But then part of the journey is also when you dig into the code, you don't know exactly what is happening. And if you look at Wikipedia, you see there are all kinds of different variants of this algorithm. So you never know exactly what is really implemented. Either you debug the code a little bit, which helps, but there are some comments, but not everything is described in detail. Or you have to find out some other way. So what I did then was, okay, I looked at the different algorithms, the different variants, and then in the spreadsheet, I just did the calculation myself to see, okay, well, what logarithm is actually used, how is the normalization done, and then you can come up with the real numbers and see, okay, now my assumption, it was this variant of that algorithm was really true. So I see the generated data fits my formula now, finally. So next thing is then, we have now the different documents represented as numbers, like with high values for words that are sticking out. And now we're just doing a clustering of these vectors, of these documents represented as vectors. And one of the most popular ones is k-means ++, so there are all these unsupervised clustering algorithms, but this one is popular because it's optimized in a way it starts with the initial vectors. So what it really does is you have some random points in space, and then you come up with all the examples, and then they shift these points until it's optimal over all the documents that you have fed in. So you choose centers uniformly, and then you, you repeat the iteration until you have an optimal clustering. So here's also a little animation that I formed, and here are the formulas if you're interested in that. So now we can try what is happening when something new is coming into our little system. So we write a new sentence. I like programming, simple enough, and then we write this into the result. We write that into the Excel file. We do the prediction. So we see here model predict with a vector coming in, and then we see here the result. So we can again just write into an Excel file, and then we see, okay, what were the clusters, what was our training material, and what is our test. So we see here lines 8 and 9. This is line 8. You see this is for Python. So it identified or made a cluster for snakes sentences, because usually if you talk about snakes, then you use also Python as a plural. You don't talk about this specific Python usually. And you see that Python, the singular, has a high value and it's very important for the network. Because if I talk about the programming language, I use the singular. So here we have like what was addressed also before in the session. If we go down to the numbers, here, okay, a simple example, but then we can really say why the decision was actually made. So we can really understand why it was classified as this or the other. Okay. So let's come to the conclusion of the first part. So for me, it was very important to not rely on a debugger or specific high-end tools. For me, it was just very, very helpful to just write things into an Excel file, do the calculations, and see the numbers on one spreadsheet, and then I really understand what's happening. And I think it can always also be done with bigger data sets, like usually you use maybe for document classification, you might use like 10,000 words or 1,000 words. You can still put that in a spreadsheet and you need to automate your analysis a little bit, but still you can do that. So when it's just like simple other modules that you use like XLS writer and okay, one trick was to the conversion from dense arrays to regular arrays. Okay, next part, then of course the hotter thing is then deep learning, because this is also more complicated, so also the challenge is higher here. And there are many examples coming up. You can easily download. Again, I didn't go to Anaconda, I just installed TensorFlow and KERAS, and here again it's important to have the right versions, so 3.5 or 3.6, and be sure you have 64-bit Python installed, otherwise it wouldn't work. And then there's a simple test also that you can run to see whether TensorFlow is really installed, where the idea of TensorFlow is you just have tensors or arrays, and you just stack them on top of each other. And this is how you build your network. You will see that later in the code also. So then I just download some examples from GitHub, and usually what's also very handy with Python, it tells you exactly what is missing, identifies, okay, you're missing this library, and then you just install that on top. And with the distributions, you get some pre-made estimators that you can run to just see whether your setup is working. And then we just, on top of that, we install KERAS. A lot of times I read that, okay, when you want to try machine learning with Python and you want to do these examples, you need to have Macintosh. But I did everything on Windows 7 and Windows 10, and it was no problem. You might get some messages that some compiler is missing, which is just a standard Microsoft Visual C++ build tools that you need, because actually what's happening here in the background when you install it, that there is a, what do you say, native compilation that also considers the hardware that you are using, so it tries to make advantage of everything your CPU can do. So this is why sometimes you get some messages also, not just about the compiler, but also other ones that say you didn't make use of this or that feature of the CPU, but it doesn't matter to run the example. And here's a simple example about Reuters data. So these are longer text messages that were collected, and they were all labeled. So for all of these, there are, to start with, 22,000 articles. And it's one of the standard tests that you can do in text classification, because all of these text messages, they are categorized. So this is about oil, or this is about cocoa, or whatever is important for business newswire news. And this comes right away with KERAS, so you don't have to look for data to try your model. It all comes with the KERAS distribution. Again, you need to import only a few libraries, and with that you can build already very, very complex networks. But then, okay, it's about my journey into digging into KERAS, and it's a little confusing about the Reuters examples, because there's basically a set of 21,000 newswires, but what is used then is then like 10,046 categories, although in the beginning, if you read it on the internet, it's 90 categories. So it's a little confusing. Everybody is using his or her own subset of the data just to show what they want to do. So what is done then also again, we cannot just feed words into a network. We also have to build a dictionary of the words that come in, and then each word in that dictionary gets a specific number. And these IDs are then put into a tokenizer, and then this is what's making the vectors for our neural network. I come to that a little deeper. So the original text is like SGML. It's like, looks like this. Something is happening to the cocoa zone or something. And what you see later, if you then debug that example, it's you have only numbers. So these are indices into the dictionary. So, but how do you come from a dictionary then to something that you can put into a network? Because the first word gets a 1 and the last word gets 10,000. That's something you can put into the network. So this is why we have tokenizers, which also come with a KERAS distribution. So it looks really simple when you look at this here. When you look at your example, you just say, tokenizer, put the sequence to a metric. So it's like the sequence comes in with indices, and it builds you a matrix out of that. So of course, then you are also interested in how does a tokenizer work. So what I did then is I made some little texts again. It's just hello, hello, and hello world, and good day. It's just 3 sentences. And then I ran the first, the same tokenizer, just with different parameters, and then I can look how the tokenizer works. So I don't spend hours trying to look at the big thing. I just reduce it to like nothing almost, and then I understand how does a tokenizer actually work. And that gives me the speed to understand the big thing, I hope. In many cases it did. So here we see, like, the first thing is the words are put into a dictionary, so it's like indices for each different word. And then what's happening in the end, I have 0, 1, 0, 0, 0, those are 3 last lines, and 0, 1, 1, 0, 0, and so it's just put hot for the indices at that position in the vector where the index matches. Okay, so this is why I have in the end then a vector that I can put into a neural network. But on the way there, I lose information. This is also the problem, exactly what was mentioned in the keynote, that sometimes little glitches in the text surprise you. You don't know why the network is wrong suddenly. But we have to be aware of what kind of information we lose on the way towards the classification. It's not by magic that something is going wrong. It's going wrong because we did something with the data. We missed something with the data. We missed, for example, that there can be typos and that hello can be written in different ways. It's still the same words. Things like that. All these extra knowledge that we have, that we also can put into our model, but sometimes we didn't. And then following up like this, we can explain what was happening. So, but this is how it looks like then with the data, with the full data. The data is split always into a training set and a test set. Here it's like 8,000 to 2,000 articles, and now coming back to the whole thing again. And the next thing, of course, is what we want to understand is the network. So first of all is how do we build the network? And this is just from the standard example that comes delivered with KERAS. And you can see here, at least, that it's very easy to build the models. It's just very few code of lines that build the whole very complex neural network. And then the rest is the training and checking the model. So here I was interested again then looking deeper also into the Reuters data, and I found that lots of these vectors for training here, they had like the 1 in the beginning. Just the number 1, the index 1. So where is that coming from? So then I had to check the dictionary, and the index 1 stands for the. So this is a little ridiculous. So I think one could get a better quality also of the classification if you would skip the word the. Could be the case. I mean, I'm sure it would be the case. Maybe I'm wrong, but it looks like it. So why that? So we can then also check the weights that the model produced and then debug on that. So we would expect, for example, that something with the index 1, so something that's much in the beginning, would get low weights. It has no relevance over all the data. We would expect that. And we can see that a little bit when we look in the debugger at the weights. We also see that we have very low numbers there. Okay, then the next step is TensorBoard. This is a more recent development also, and it can also be easily installed. But one has to make some extra changes because the code has to be augmented with namespaces or names of scope, as it said, so that the network really sees, or that the TensorBoard really sees what belongs where. And then you can actually also have a very nice visualization of the network. You can see the different layers, you see the performance, you see the accuracy going better and better. And then I hope you can see that here also it has a very good representation of what the network learned and where it has a problem learning, where it has a problem getting the correct classification. So you can see, for example, there's on the upper right side, there's an 8, which is similar, or it was misclassified as a 5. It's very close to a 5. And you see in the middle, more or less, you see a 3, which looks very close to a 5. So this helps us a lot to understand what the network is really doing and where it has its problems also, and it explains then also some misclassification. Okay, so as I said in the beginning, it's a little bit a journey for me. It really helps to understand a lot. It's also good for projects that I'm doing because sometimes it's not the classification in the end, but it's to prepare text for search, for example. So all the algorithms that we have for text classification, like TF, IDF, or their word of bags, and all kinds of these things are also available with the Python libraries, but sometimes you don't want to use them for text classification. Maybe that's the next step for me, and sometimes in some business at least. So, but understanding the challenges also, like with misspellings, for example, it helps to dig into these modules and then see what they can do and where are the challenges also. Okay, so what I learned is I can debug, I can learn something like that, I can export the data, and I can use new tools, but I recommend not to start with TensorBoard right away. I recommend to start with simple networks, and I recommend to crunch down your problem so small until you really understand down to the number what is happening, and then go back to the real data again. Okay, so it's a little bit like a brute force approach, I could say, because I just did not care. I just wanted to get it run, and if it runs, then I look into the details. Then I come back there. I reduce the problem until I understand every bit, and then I can extrapolate, and then maybe I don't need to check every single number again anymore, but I have an idea what can go wrong also. All right, so thank you for listening, and well, now I'm ready to many questions.